So now on to the third topic, action-reaction forces on different masses. So for this one, we're actually going to reflect back a little bit to Newton's second law of motion. But right now we are on page 5, looking at your student note sheet. So highlight your note sheet for the things that you think are important here. So we're going to talk about cause and effect. So if I try to push on a small stack of note cards and a large textbook with equal forces, what's going to happen? Will the effect on the note cards be the same as the large textbook, or will it be different? Well, most of you are going to recognize that it's going to be different. I may easily be able to push the note cards across the table, but if I use that same force that easily pushes the note cards, the textbook might not even move. So what we're kind of thinking about here is if you have two equal large forces acting on two different masses, one being small and one being much larger, you should recognize that the force on the small mass will cause there to be a larger acceleration, and that will maybe a larger visible effect. And the force on the larger mass will result in a smaller acceleration, and so that will have a smaller visible effect. So this all follows from Newton's second law of motion, where A equals the force divided by the mass. So if the same force is applied, the smaller the mass, then the larger the acceleration. And since action-reaction pairs, we are talking about the same force acting on two different objects, we can end up with very different accelerations. So for example, when a bug and a bus hit each other, your reaction force pairs are bug hits the bus and the bus hits the bug. But if these forces are equal, which object's going to have a larger acceleration? Is it going to be the bug or the bus? Well, I hope you said the bug. So when this bug has a huge acceleration, the actual structure of the bug can't handle it and it gets smushed. So when we think about the bug hitting the bus, a lot of people tend to think about the fact that the bus gets smushed and the bug gets smushed and the bus does not. But they neglect to consider the fact that the forces are the same because they look at what actually happens, what the effect is. Okay, and I think that's the thing that gets most confused about this law. So even though a lot of people know this statement about the two forces are equal, they forget that with the forces being equal and the masses being different, we're going to have different accelerations, and that will lead to different visual effects. So I've worked this all out in numbers in the purple table on the purple packet. Some of you who are mathematically inclined will find this very helpful. Others will not find it helpful at all, but I've kind of defined a small mass and a large mass and worked through the math to kind of prove it to you. But I want to show you a short video about Newton's third law of motion, and I'm hoping that this will explain it to some of you a little bit better. It may not, but hopefully most of you will get something out of it.
There are a lot of misconceptions out there, and this is a video about one of the most common ones. So I went around asking people, what makes the moon go around the Earth? And they told me,
the Earth puts a gravitational force on the moon.
But does the moon put a gravitational pull on the Earth?
Pull on the Earth? Yes, it does. Hence we have tides, etc.
The moon pulls on the Earth too. It affects like the tides and women and stuff. It does. Very powerful, this thing.
Does the moon pull on the Earth?
Probably that as well, yeah.
So what I want to know is how does that force that the moon exerts on the Earth, how does that compare in terms of size to the force the Earth exerts on the moon?
Well, I'm no scientist, but I think that one would be more powerful than that one.
It's got a greater force coming from the Earth because it's a greater mass.
Because the Earth probably has more mass.
Because it's a bigger mass. I thought greater mass equals more force.
Does the moon pull on the Earth?
Yes, but a lot less.
Yeah, not as much as the Earth pulls on the moon.
Yeah, but a little bit.
But not very strongly.
Yes, but much, 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 much smaller.
Because of its mass,
less
its
mass.
size.
Because it's smaller, it's much smaller than the Earth.
Because it's smaller.
Is it small?
Allow me to let you in on a little secret. everyone got it wrong. The force that attracts the moon to the Earth is exactly the same size as the force that attracts the Earth to the moon. So what's going on here? Why did everyone get it wrong? Well, I think it comes down to cause and effect. The effect of the force on the moon is quite clear. The moon goes in circles around the Earth. But the effect of that force on the Earth is basically negligible. The Earth barely wobbles at all. So people interpret this negligible effect as indicating there's very little force affecting the Earth. But that is forgetting the third key piece of the puzzle, which is inertia. Inertia is the tendency of mass to maintain its state of motion. Since the Earth has a greater mass, it has a greater inertia, and so even with the same amount of force on it, it doesn't accelerate that much. Now the funny thing is, many of the people I interviewed could state Newton's third law, which is every force has...
Oh, an equal and opposite reaction.
Something about Newton's law doesn't seem to fit into that. You're good at this.
Which Newton's law are we talking about?
The whole equal and opposite force thing. Yeah, that one.
So tell me what you're thinking now.
Well, one would think that if the Earth is putting a force on me, I would be putting an equal force upon it.
So why didn't they apply it to this problem? Well, I think they may have memorized the words, but not really believed Newton's third law in their core. Did they really feel it in their spleen? I don't think they did. So, allow me to try to convince you, all of you, spleen included, that Newton's third law really is true. Let's consider two objects. Initially, they have the same mass, 1 kilogram each. So obviously, the gravitational force of attraction must be the same on both of the objects. Now let's add a second kilogram to the first object. The force on the second object will now be twice as great because that 1 kilogram is attracted equally to each of the kilograms in the first object. But what is often forgotten is that new kilogram is also attracted to the second object, meaning that the total force on each object is still the same. They're attracted to each other with an equal and opposite force. We could add a third kilogram and we would find the same thing. The force on both objects is still the same, even though the object on the left has 3 times the mass of the object on the right. So we can see that no matter what the mass, any two objects will have the same gravitational force towards each other. Can you feel Newton's third law in your spleen now? It should settle inside you and become a part of you.
Right. So now when you hear students from my previous classes talking about understanding something in your spleen, you know what they're talking about. Now, hopefully some of that made sense to you. If the whole idea of adding the masses didn't make sense to you, it's okay. It was just another way of presenting this same idea. So we're going to go over a couple of problems now on page 8, number 5. So I'd like to ask you to pause the video, do these 4. Remember, the forces are going to be equal, even if you see different accelerations, and I'll go over the answers in a moment. So A bullet is loaded in a rifle and the trigger is pulled. The force experienced by the bullet is equal to the force experienced by the rifle. And the resulting acceleration of the bullet is greater than the resulting acceleration of the rifle. So the smaller mass has the greater acceleration. B, a bug crashes into a high-speed bus. The force experienced by the bug is equal to the force experienced by the bus. The resulting acceleration of the bug is greater than the resulting acceleration of the bus. So again, the smaller mass has the larger acceleration. C, a massive linebacker collides with a smaller halfback at midfield. The force experienced by the linebacker is equal to the force experienced by the halfback. And the resulting acceleration of the linebacker is less than the resulting acceleration of the halfback. In this case, the linebacker is bigger. It says he's massive, and the halfback is smaller. Letter D, the 10 ball collides with the 14 ball on the billiards table, and we're going to assume equal mass balls. The force experienced by the 10 ball is equal to the force experienced by the 14 ball. And the resulting acceleration of the 10 ball is equal to the resulting acceleration of the 14 ball. This time the masses were equal, so they're going to have equal accelerations. So hopefully you did okay with that. And for additional practice, I'm going to have you do the MOP app part 2, NL12, which is the final MOP app in this third law of motion. And this is going to practice some action-reaction pairs as well as which one has the greater acceleration.